Okay, let's get started. So we'll see. Last time we talked about the Simplex Manifold. No, Simplex Riemannian Manifold. Today I'm going to talk about the Simplex Manifold. So I think I have updated lecture note. So I think you guys should look at the updated one. Even 10 minutes ago I already changed a little bit on the lecture note. So you should take a look at. Yeah, each time I find a typo and so on, I always correct and then put it into the e-learning updated one. So you should take a look at it. And then, so homework 5 is very important. So even though most of them are very important, but this homework 5 is very important. You should, except problem 1. Now problem 1 is just coverage identity, but problem 2 and problem 3 are very important. So you guys should spend some time to think the problem. Okay, so today we are going to learn a Simplex Manifold. So Simplex Manifold. So usually before this year, always like I said 2 hours or like a 45 times 2. So I didn't include Simplex Manifold in the content, but now we have 3 hours, so I decided to include Simplex Manifold because it's important. Simplex Manifold is Simplex geometry. Geometry. The history of simplex geometry is longer than older than the Riemannian geometry indeed. Riemannian geometry is the idea was first initiated by Riemann, as I mentioned, but simplex geometry is initiated by physicists. I thought the simplex geometry is initiated by Hamilton, but it turns out that it's not the case. When I prepared this lecture note, I just searched a bit of history. It turns out that Legendre, so as you know, Legendre transformation, Legendre and Poisson have reached actually the simplex geometry, indeed, and to study the classical mechanics, or maybe just equation, motion, whatever, the physics of the planetary moves. So, I mean, planetary moves are, of course, studied deeply by Kepler a long time ago, but they tried to formulate in modern language, Legendre and Poisson. They reached simplex geometry 1808. 1808. And then Hamilton indeed actually reformulate what the Legendre and Poisson did in terms of, so nowadays called Hamilton formalism. And also, I mean, Cauchy also, Hamilton is, I think, as far as I know, I may be wrong, is from Edinburgh in the Scotland, or it's very subtle issue, but the UK. I shouldn't say England. It's a Scotland. I mean, they have some very historical, issue about the land. But Edinburgh, and it's a very nice city. I visited once. So in summer, its daytime is very long. In winter, daytime is only like 5 hours only because it's located north. It becomes light at 10 a.m. and it gets dark in 3 p.m., something like that in winter. But it's historically a very beautiful place. And Hamilton himself thought the quaternion is the most brilliant discovery of among his discoveries. His academic achievement, but one of them is this Hamiltonian formulation of this classical mechanics. I mean, that's the physicists actually started symplectic geometry. At that time, there's no term symplectic. Symplectic come from maybe before going then. Yeah, okay. Symplectic come from the word coming from the while. So while it's very classic book called the classical. I think his book is Classical Group. His famous book for group theory. It's a very classic. So the term coined by Weil is a symplectic group. But even before then, symplectic geometry has initiated by physicists. And then a lot of people has contributed, even in 19th century. Poincaré is of course one of them. And then entering 20th century, it becomes richer and richer, including integrable system, Lie group, dynamical system, and so on. It's a very deep subject. And then today I'm going to talk about only the relationship with classical geometry and simplex geometry. There is a classical book by Arnold. Arnold, what's the name? Mathematical Method of Classical Mechanics. That's a wonderful book. I highly recommend you to read. Arnold, he's a Russian. Who pushed the simplex geometry forward, and including dynamical system and integral system. In 1984, the revolution has found there is a revolution in simplex geometry made by Gromov. He's Russian. Gromov. He used to study Riemannian geometry before 1984. 1984, he made a breakthrough in simplex geometry. Nowadays, he gave a modern viewpoint of simplex geometry. And from there, this book is again interpreted by so-called Witten in physics by using so-called string theory, and nowadays the simplex geometry is the very how to say. Has developed. Since then, the simplex many people have joined, and it becomes deep subject. In the physics language, it's called air model. We need a topological twist, the so-called topological twist. It's called air model. And the simplex geometry is very difficult. It's a deep subject. And also another contribution is made by 88, another genius by Floor in Simplex Manifold. Since then, this work is also partially interpreted by Witten by using so-called I'm not going to bother. And personally, currently, I'm working on this simplex geometry or A model, but it's a very deep subject, and lots of things has not been understood, and lots of things has not been formulated even in mathematics. Even physicists struggle to deal with this simplex geometry. But mathematicians, of course, hard to analyze. Even physicists is struggling. Lots of books are written, but still, we need to do lots more effort to make it mature subject. Anyway, so it's a very deep subject. But what we are going to learn is very beginning from simplex geometry. So I just want to tell it, and so if you're interested, you should first start with Arnold's book. That's a wonderful book. Yeah, when I was your age, I also read through. I found it very fascinating. Okay. So what did this Legendre, Poisson, and Hamilton, and Cauchy did? I mean, after Hamilton, Cauchy has written for a bit more, like like how to say, more transparent formulation for Hamiltonian mechanics. So let's first start with Hamilton formulation. So classical mechanics. So let's start with the action with potential. Sorry. Lagrangian, where Lagrangian is written, he describes the particle with mass m. This is kinetic energy, and with potential v. This is Lagrangian in the action, and we assume q is a coordinate. Oh yeah. So thank you. So now instead of x, I'm gonna use q in this lecture due to historical reason. Instead. So q is a coordinate. And then Euler Lagrange equation, by using Euler Lagrange equation, you get the Newton equation. Oh my goodness.
It should be
it should be minus. Sorry, it should be minus. Thank you very much. So the election is wrong. Sorry, it should be minus. And then again, so the Hamiltonian show up as a Legendre transformation. So this is Legendre transformation. So then now it's become plus 1 over m p squared plus b of q, where p is defined as m times q dot, the vector. So this becomes Hamiltonian. And as you can easily see, the energy is conserved. Energy conservation, you just take a derivative 1 over m pi dot plus q dot. So, and then you just plug that one into here. What you get is q dot. I'm going to omit the lower subscript q dot. That's what you would get. Okay, so then again plug that Euler Lagrange equation into here, and this is equal to 0. Okay, so this therefore energy is conserved. It's very simple. And then what is the equation motion? So how do you get the equation motion from Hamiltonian? So given the action, so you just take the how to say, whatever steepest anyway. So you just find the configuration that minimizes this action is different. That's our Lagrange equation. So okay. So but given a Hamiltonian, how do you get this equation without knowing Lagrangian? So that's very easy to do. So that's called Hamiltonian. So that's what Hamilton found, is that the q dot is equal to P dot J. Okay, so that's the Hamiltonian canonical equation. So, how many you didn't learn this one? Didn't learn. Okay, everybody has learned. Did you learn this one? No. So, how many of you learned this one? Just raise your hand. Okay, everybody. Okay. So you can derive this from this one to here. Okay, by plug this one to here. Hopefully. So, and then Euler-Lagrange equation. So this is indeed Euler-Lagrange equation is the following. So just everything rewrite. Everything P and Q. H, P and Q, dt. So you can just take this one as an action and just variation principle, you get this one. Okay? The Hamiltonian canonical equation. This is Euler-Lagrange equation, this is Hamiltonian canonical form. Hamiltonian equation. Okay. And at the end of the day, so this Cotangent, Hamilton found a Cotangent. This Cotangent algebra, and Cotangent algebra show up in the so-called hyperkiller manifold, hyperkiller geometry, which is a part of simplex geometry. So it's kind of coincidence, maybe coincidence, but it's quite amazing. Anyway, so what Legendre did is as follows. So just here we write this, just introduce so-called phase space, which just the 2n-dimensional manifold of dimension 2n, and whose coordinate is just a p1 dot pn q1 dot qn. So you just combine moment and the coordinate. And then, so he just write down the, oh my goodness, I already made a mistake. Seems like so as I mentioned, and here I just need phase space is R to N, and we just put some standard metric ds square is just a standard metric dpi plus dqi and dqi. Okay, so standard metric. Now you can just consider that some gradient flow. So gradient vector field is only defined by using the metric. So this one is just a as a vector, it becomes like this way. So gradient of H, the Hamiltonian is just this one in this phase space. And then he just introduced the following matrix 1 to n minus 1 to n, 1n. So identity matrix, n by n identity matrix, and the off diagonal, minus 1, 1. Okay? And then, so the Hamiltonian equation is written in terms of the space variable x, in terms of like this way. So this is what not Jacobi, sorry. This is what this equation is written. So this is, oh sorry. So this is not H. Sorry. I think my lecture notes is full of typos. Sorry, I will change later. So this nabla is just gradient. Sorry. So can you see that? So once you plug in, do you see? This one leads to that equation. So for instance, let's take a look at P dot Q is equal to minus 1, 1, del H del P, del H del Q. Okay? So that if you multiply the ordinary matrix multiplication, you get the Hamiltonian equation. Okay? So this is written in Legendre. 1808. Okay. To step further, so what Poisson did is so-called Poisson introduced Poisson bracket. So Poisson bracket, so the f and g are function of the phase space, and then what Poisson did is introduce so-called Poisson bracket, and Jij function if function Jg is equal to sum over n, j equal to 1, j minus. So it's very classic, very what you have learned in classical mechanics. And then so this is Poisson bracket. And then what the Hamiltonian equation can be, how the Hamiltonian equation look like is this one. So that's what Poisson did. 1808, 1809, 18 or 09. Looks like a very simple. Looks like there's no geometry, but it turns out it's very deep. So you have learned this one, right? In classical mechanics. Okay, so that's a reminder. And so what we are going to learn is how this Poisson bracket and so on will show up by using simplical manifold. So, what is the Simplex manifold? So we'd like to create something. So what it show up is you just consider some two-dimensional phase space which combine. Are you okay? Q and P, and then introduce some matrix which is minus 1, 1 of diagonal one. That will give you the Simplex geometry. So the Simplex geometry is as follows. So what is the Simplex manifold? So eventually we will get there. So just wait a moment. So M is a smooth manifold with the two-dimensional smooth manifold, and omega is two-form. And then, so the omega has to be 0. It's closed. Omega is closed and non-degenerate. And it's non-degenerate. And omega is non-degenerate. So omega is non-degenerate means as follows. So given omega, so this induces a map from, so this becomes isomorphism. So namely, so x, the vector, I think, yeah. becomes isomorphism, or namely, so given a vector field X, which is the vector field, which is a section of tangent bundle, is mapped to one form. Okay. So it's two forms. So if you contract with vector field, it becomes one form. Okay. So this is one form. Okay. This is one form. In other words, non-degenerate means that any x in any vector field, there's a y such that the omega xy is non-zero. That's the non-degenerate means. If you're sick, it's better to take a rest. Are you okay? Okay. In particular, so if M is if M is closed, so non-degenerate means the omega wedge dot omega becomes volume form. How many copy of omega? N copy. So if it is close oriented, sorry. Close oriented, then it becomes, this is equivalent to non-degenerate indeed. So this is, and with this condition, omega is cosine, with this condition, so the condition for omega is this one. What was the color choke? So the condition omega is this one. Yeah. So this one is called simplex form. And the pair M omega is called simplex manifold. Simplex manifold. Yes.
Is this one just need exist such a y belongs to x m or for anyone? So its existence.
I'm sorry?
I mean, is there only required that there exists such a y or for any y? So for this.
So there exists a y. Yes. It can be some, there is some y such that the omega x y can be zero. Can be zero. So in other words, in locally, okay. Anyway. So what's simplex manifold? So here there is no distance. Of course, if you can include metric, but the simplex geometry just can consider only simplex form without introducing the metrics.
So is there any relation between metric and the two form omega?
Yes, two form omega. You can introduce some metric, and you can just relate omega and the metric. That is called Kähler manifold. So one can introduce so-called metric M and G and omega, and let's see. Okay, so M is 2n dimensional, so it can be complex actually. And so-called, so you just introduce so-called almost complex structure. This is called almost. I mean, okay, I can include the appendix for complex geometry. Okay, almost complex structure. And this is metric. And G is equal to omega J. J is tangent space, is mapped from tangents to tangent space such that J squared is equal to -1. This is called almost complex structure. So with this condition, this combination is called Kähler manifold. And the example is CPN. It's very important example, CPN. That's a Kähler manifold. I'm not going to go into the detail, but since she asked, so I just explain. But I will add appendix for complex geometry that explains this one. So I'm not going to talk at this moment. So, and what the Simplex manifold? The Simplex manifold is, roughly speaking, you can just integrate this omega in a surface inside a two-dimensional surface. Inside a Simplex manifold, and you can integrate. So this is area, and this can be understood the area of sigma. And since this is closed, so what does closed means is that even though you just, so there is an M here, so M, so it's a two-dimensional manifold, and there is a sigma, whatever, just schematic diagram, sigma. Even if you deform this sigma by I didn't say anything about the homotopy and so on, but by one parameter, you just deform this sigma by whatever method. You just deform in smooth way inside M. So let's call sigma prime. So continuously, you can just continuously move inside M. Okay, it's like how to say? It's called Chabon. Oh my goodness. In Japanese, oh my goodness, I already forgot everything. In Japanese, what is it called? Is it Chabon? It's Sabon. In French, it's called Sabon. But anyway, so let's not talk about it because I cannot do that. Oh my goodness, I already forgot the English name. Anyway, the kids, when you go to park, kids just put the soap with water with soap, and it's lots of someone. What is it called? I already forgot. Anyway, so the contents, you can contents deform inside M sigma prime. Since so the d omega is closed, which means that the area, if they are related by continuous way, area sigma okay. So if they are related to by, you can just deform a continuous line inside a M, so the area of sigma prime and area of sigma is the same because it's closed. So as I mentioned, so it's continuously moved, so you can just consider sigma cross I, and the omega is of course 0 by Stokes theorem. And by Stokes theorem, the area should be the same. Okay, so what Simplex manifold is that you can define the area in such a way that even if you continuously deform the two-dimensional surface, the area does not change. That's what you mean. Okay. It's very simple definition, but this simple definition will lead you to very deep subject. So the simplest example is again R2n. I already erased. Whose coordinate is P1 dot of Pn, and Q1 dot Qn, that's a coordinate, and the omega is dpi, which dqi. So this is the simplex example. Another simplest example is cotangent bundle. So cotangent bundle of n, so T star n. So this cotangent bundle can be understood as, so n is a n-dimensional manifold, smooth manifold. And then you can consider T star n, and then we consider the local coordinate. We can just consider, so the n, so I just draw the schematic figure. So there is an n, and there's a at each point you have a fiber. At each point, this is the Russian way, or maybe I may be wrong. Russian way to write down fiber. I realized I learned it from Okunkov. He's a metallist. So this is n, and this is fiber, and I just consider the local open patch whose coordinate is Q1 dot Qn, and this local coordinate is P1 dot Pn. So in other words, P1 can be understood as dqi. Okay? So it's a cotangent bundle. Therefore, the base, it can be understood dqi. Okay. But instead of one form, I just consider as they're just coordinate. And then omega locally can be written again as dpi, which dqi. So the dimension T star n, so the cotangent bundle itself has a manifold structure, has a smooth manifold structure, and it's 2n-dimensional manifold. And the local coordinate around this point is Q and P. It's spanned by Q and P, and this is simplex form. Okay, it's very simple. And this is one of the example. What is the n in this case? What is the n? So you just consider this one as a cotangent bundle. What is the n? You just consider R2n, this R2n as a cotangent bundle of something. What is the something manifold? Of course. So this can be understood as cotangent bundle of Rn. Okay. You guys really okay? I mean, video is recorded, and I will post a video. If you're sick, it's better to take a rest. Go dormitory and sleep. That's the best way to take a rest. Okay, I have written the. Okay, I don't think it's a good example, but as I mentioned, so this CPN has the Kähler manifold, so therefore it's CPN can be understood as simplex manifold. And then in the lecture notes, example 7.3, I have explicitly written down omega. It's called Houdini study form. Anyway, so that's a bit advanced. I'm going to skip. And there's an important theorem. So the theorem, which is very, very helpful, even though you need a proof if you're a mathematician, but I'm going to skip the proof. Double theorem. You can take a look at the Arnold's book. So if m and omega, so the reason why the CPN is compact, closed, okay? Whereas the Rn or cotangent bundle is not the compact manifold. It's not compact manifold. So the reason why I put the example of CPN is the CPN is closed and the compact. So whereas the Rn and the R2n and the cotangent bundle is not compact at all. Is a simplex manifold. So then, so pick the point P. Let's see, simplex manifold M. Put the point P, and you can always take the local coordinate. I shouldn't use P actually. I should use X actually. Let's point of X. And then there's a local coordinate such that Q and P. Local coordinate is a two-n dimensional. Then you can always, given any point X, the theorem said the double said that you can always there exists always local coordinate Pi P1 dot Pn Q1 dot Qn such that the omega can be written in terms of dqi with so dpi, sorry, dpi dqi. Okay. Given a simplex manifold, locally you can always bring dp with dq. That's what the double theorem mentioned. It's a very nice theorem. So therefore, locally always bring to this R2n. Okay? R2n. Locally you can always look at even CPN. That's what it means. The CPN has some simplex manifold who is 2D metric, but the locally it looks like just a phase space R2n. That's what double mentioned. It's a very nice theorem. And then given the manifold, you always consider the map. So M and N. What did I say? N? Okay. So both simplex manifold. And you just consider a smooth map. Smooth map. So such that the F star. So if you're given a smooth map between manifold, you can always pull back the simplex form, the differential form. Okay. The push forward is always like a vector field and so on. But differential form is pull back. So F star omega n. If this omega m, then F is called simplex morphism. It's called simplex morphism. So pullback or simplex form is exactly the original. That's what it means. So So this condition, this simplex morphism is very strong. So that the dimension of M has to be less than or equal to dimension N. Okay. So that's intuitively clear, right? So R2N is mapped to, you can always embed R2N, okay? Such a way that of course, locally, everything looks like R2N, okay? Simplex manifold. So you just study locally what's going to happen. So then you just define P1, Pm, Q1 dot Qm. You can just take a coordinate such a way that the Pm 0, 0. This one is n minus m piece, maybe -1. I don't remember which one is the correct. Yeah, this is correct. Okay. Then standard simplex form can be pulled back to R to M. Then they go inside. Okay. But if you if M, so here M is less than or equal to M. So if clearly you cannot pull back. If this is a case, clearly you cannot pull back the simplex form. There is no extra coordinate in the original space. You cannot pull back. Okay. What is the example? Oh, did I make? Yeah. So the example, Simplex Group. So this was coined by. This name was coined by Wang. From a while. Wow, genius. Personally, I'm really fascinated by the work by Wow. There are lots of people. There are lots of mathematicians who did great work. There are lots of physicists who did great work, but there are very, very few people who can do the work both in math and physics. Wow is one of them. Poincare is one of them. Very few people. So R to N omega. So omega is just standard one over there. And then so simplex manifold, simplex group is the following. So it's more like a where J is equal to -1, 1. Okay. So this is the simplex group. Or you can put the minus, since I connection, I just put the minus sign here and the plus sign here, but whichever is okay. It's intuitively clear, as I mentioned, so the P and the Q is paired. So here, if you have a, let's see. Essentially, so what simplex? Let's see. The reason why you have here wedge. So what you can do is dp and dq And then let's see, minus dq and dp, which, and that's how you obtain the simplex form. And somehow I got a minus sign, but I don't care about the signs of simplex form. dq, which dp, which is 2 times minus 2 times original simplex form. I don't care the sign. So the reason why I have a j, okay, you have a j is minus 1 form is you just have a pairing between p and q in skew symmetric way. So that if you take the one form by this matrix and take wedge product, what you end up with simplex form up to some coefficient.
By GL 2 and R, didn't you mean G is a matrix?
Yeah, sorry. I think I should mention. So this one is just it's just a 2n times 2n, 2n by 2n matrix. Matrices as a set of 2n matrices with determinant is non-zero. So this is what you mean. Do you understand?
So why do you write dp dq it's like a
One form?
It's like a vector matrix.
So what? Okay, let me explain a bit more detail. So G is 2n by 2n matrix. So P and Q are the coordinate of the R2n, and G acts on it. Okay. So G is 2n by 2n matrix. So this is 2n, and this is 2n. But you end up with some whatever. G dot P and G dot Q. Okay. Well, we are interested in the pullback. So dq, dp, sorry. So d g dot p, which d g dot q. Hopefully you can understand what the difference between Q and G, my handwriting. So this is the new the simplex form, which is pulled back. Okay. So let's see, R2n is G, R2n. Okay. And so the simplex form is dp, which dq. And you just pull back G star omega. So this is G star omega. And it has to be equal to the dp with dq. I think it's better to do the n is equal to 1 case. I think n equal to 1 case is more illuminating. I think n equal to 1 case is more illuminating. Okay, so this is just 2 by 2 matrix which satisfy that condition. Let's see, how should I? Yeah, so the simplex form can be obtained by let's see, just the product. So this form can be obtained by G minus 1 1 0 0 G transposed G So this is equal to up to some constant, up to I would say minus 1/2. Okay, minus 1/2. This is equal to this guy. Okay. Do you understand? Okay. So then, if this condition is satisfied, this is equal to 1/2. Let's see. dp dq transpose g transpose minus 1 1 0 0 g dp and dq. Okay. If this condition is satisfied, this is equal to original one. dp dq minus 1 1 0 0 dp and dq. Okay. And then, so what you end up with minus 1/2, this is equal to dp wedge dq. Okay. Therefore, pullback is equal to is equal to original simplex form. Okay, so that's how the well-defined the simplex group. Yeah, so the simplex group is kind of some kind of SO type, SO or U type symmetry, U-type symmetry. So as I mentioned, SON is just preserve the metric, the standard metric that acts on Rn as an isometry in terms of standard metric. Standard metric, okay? And also UN acts on Cn as a standard metric. Standard metric is a think this is dz, dz bar, okay? dz bar I, okay? So as an isometry in complex word, UN. The simplex amount of simplex group is the kind of isometry. I shouldn't use isometry because it's not Riemannian manifold, but you understand. You just preserve under this symplectic group rotation the simplex. Instead of metric, simplex form is preserved. That's the meaning of simplex group. Okay. So, and there is an important again theorem. So therefore, yeah. So this is more the. So there is given a one parameter family of simplex manifold. So T is the some so T is one parameter family. Some R, some segment in R. So omega is deformed, which means omega is deformed by one parameter family. Omega can be deformed. But in such a way that as a cohomology, so if the cohomological omega, whatever say, T are all same in the same element in M. Drum cohomology. So as I mentioned, so given a drum two form inside R H2 R drum cohomology, one can always add one form plus d lambda, where lambda is a one form. One form. Even if you add it as a cohomology, it doesn't change because it's quotient. It's a quotient group. So therefore, omega is the same as a cohomology is the same as a cohomological element inside H2. Okay. So that's what it means. So as cohomology does not change. Then, so given that this one parameter family of the simplex manifold, there exists as the simplex morphism. The family of simplex morphism. This is the. Oh gosh. Yeah, simplex morphism is in such a way that the simplex morphism such that the phi 0 is equal to 1 and phi t is equal to phi t star omega is equal to omega 0. I think I should use maybe yeah. So this means the given a manifold, a simplex manifold M. Okay? And then at a point, given a point, you have the coordinate in such a way that the P and Q, whichever you want, the omega is written dP, which dQ, essentially roughly speaking. But as a simplex manifold, there is a one parameter family that deform this coordinate, essentially, whatever way. So another, let's say Qt and Vt. So omega t is written dP t, which you cannot see blue line. Sorry, I should use another color. But unfortunately, there is no color choke. Where's color choke? Unfortunately, there is no color choke. I think during the break, I will steal somewhere from color choke from somewhere. So just bear with me. Such that the omega t. So this is, let's go omega 0 now. Omega t is dpt, which dqt. So in the simplex form is deformed so that the locally P and Q coordinate will be modified. Okay, and you have to patch globally. Okay, you have to patch globally, but there is some simplex morphism in such a way that the simplex morphism that change the coordinate by one parameter family. That's what it means. Okay. So therefore, model study these theorems, and one cannot change simplex form intrinsically. So given the simplex manifold, you cannot deform if the cohomology is different. Cohomology is the same. Okay, if the same the simplex form sits in the same cohomology, you cannot deform the simplex form. You can change the cohomology class maybe, but then there must be different simplex manifolds. Hyperkähler manifolds okay. I will give you some example. Just a bit different simplex manifold. So maybe a bit detour. If you don't understand, that's totally fine. As I mentioned, M, G, omega, R, J. So this is the Kähler form. As a complex manifold, this is complex complex dimension is n. And so it's like a CPN. It's like a CPN. J is essentially locally can be written -1, 1 in tangent space, in real tangent space. So that the J square is apparently -1, right? -1 apparently. So this is almost complex structure. Essentially, what J does is, for instance, if you look at the Cn goes to Cn, Z is mapped to Z bar. So that's why it's called. This is J. it's a bit abuse of notation. Okay, let me abuse a notation a bit. I mean, J really acts on tangent space to tangent space, but therefore this is abuse of notation. Let me abuse the notation. So essentially this J almost complex structure is a complex conjugate. Okay. So therefore, so what I mean is partial x plus I delta y is mapped to like this way. Indeed, this one is mapped to this one, and this one is mapped to this one. Indeed. And if you do the second time, what you end up with is this one. One more time. So this is called the almost complex structure. And then the Kähler metric, so this is metric is related to omega j in this way. Anyway, so this is called Kähler manifold, but you can have three complex structure. It's called three complex structure, almost complex structure, omega ijk. They satisfy Cotangent algebra. Cotangent algebra. And then the manifold with metric and omega, and then omega I, omega j, omega k, and ijk is called hyperkähler manifold. It's a hyperkähler manifold. Manifold. You don't need to understand this one, so it's very important, but it's too advanced for you guys now. For instance, the important example is R4. In R4, one can take the complex dx1 plus I dx2 is a complex coordinate. dx2 plus maybe I should said xi, x1 plus I x2 and x3 plus I x4 can be understood as a complex coordinate of R4. We just identify C2, right? Okay. But there is another combination one can take, x1 plus I x3, x2 plus I x4. This can be understood also complex coordinate. So there's a three way to introduce complexification. That is related to I, j, and k. And if you appropriately choose the sign of the, this is not correct sign. I already did exercise. I just being schematic. X3. So these are the three ways to introduce complex coordinate in R4. And it satisfies so-called Cotangent algebra. Cotangent algebra, you know, right? Ij is equal to k, and then if it's in cyclic, I squared is equal to minus 1. Okay? J squared is equal to 1. So that's called the Cotangent algebra. And there are three complex coordinate, complex structure. That's called complex structure associated to the R4, and they satisfy Cotangent algebra. So therefore, there's a and the simplified form associated omega I is, as you can easily see, dx1 wedge dx2 plus dx3 wedge dx4. Okay? dx4. However, one can also change omega j is, of course, as you can easily imagine, dx1 wedge dx3 plus dx4 dx2 wedge dx4. Okay? And so on. So the omega k is also defined in the similar way. So that's the simplest example of hyperkähler manifold. And given some hyperkähler manifold, for instance, the famous compact example R4, T4, as you can, I made a mistake. T4, you just question Z2. And here, you can have different different simplex form, which are not connected by this one parameter family. Okay. Omega in T4, omega I, j, k are not connected by one parameter family. Okay. So that's a counterexample of this one. Sorry, not counterexample. Sorry, I shouldn't say counterexample. Since omega I, j, k do not sit into the same cohomology class. They are not sit in the same cohomology class. Therefore, they are not related by one parameter family of simplex morphism. Okay? So here, if they sit in the same cohomology class through the one parameter family of simplex morphism. Anyway, so this is just detour. Since I'm working on hyperkähler manifold and simplex geometry and so on, so I'm very fluent on this issue. Okay, so let's finish Lagrangian and then move on. Should I erase somewhere? Okay. So Lagrangian submanifold. So this Lagrangian is nothing to do with Lagrangian submanifold. So this Lagrangian submanifold, this Lagrangian is nothing to do with this Lagrangian I have written in the beginning. So Lagrangian submanifold is a particular submanifold in simplex manifold. So M inside a simplex manifold. So assume this dimension of M is 2n dimensional. And then, so this one, Lagrangian submanifold has to be n dimensional. So it's a half-dimensional submanifold in such a way that let's call submanifold L. So L restricted, omega restricted L is 0. Do you know what it means? So for instance, let's consider R4. R4 is a very good example. So let's consider some particular simplex, let's consider this local coordinates P1, P2, and Q1 and Q2. Let's consider such a coordinate. And the simplex form is again dP1, which dQ1, plus dP2, which dQ2. Okay? That's the simplex manifold we will consider, R4. So this is the simplex manifold we consider. Okay? So then, Lagrangian submanifold two-dimensional. Can you come up with Lagrangian submanifold inside R4 here? Omega restricted to Lagrangian submanifold is always 0. What does it mean? Can you come up? Very simple question.
Restrict Q1, Q2 constantly equals to 0.
So what he said is as follows. R4 is schematically just look at the P direction and the Q direction. This is two-dimensional and two-dimensional. I cannot draw four-dimensional. So if Lagrange sits in, what he said is so submanifold, two-dimensional submanifold sits on Q. Okay? Suppose they sit on Q. Tangent space in here is always can be written dQ1 and dQ2. Okay? Even if you act whatever dQi, this is always 0. Because you can contract dQi here, but the other part is dP. Okay? You cannot contract dP and dQ, right? ddq, the other q. So therefore, it's always 0. The same thing happens. So if you do pick the Lagrangian submanifold here, p direction. So the omega restrict this yellow submanifold is always 0. Okay. However, if you pick the middle, the things will change. So here, essentially, you cannot read it blue so much, right? So let me finish writing. Okay. So the vector field is generated by del del P plus del del Q. Okay. Therefore, symplectic form will see I have to be a bit careful in this case. Is this 0 or not? Looks to me 0. It should be 0, right? Yeah. So this is 0. This is Lagrangian. Okay, this is 0. I just want to come up with some nice example that say this is no longer 0, even though it's 2-dimensional. But you can definitely pick some nice combination. For instance, dp1, dq2. That's not the right example. Maybe dp2, dp1. Then it's okay, right? Then it's no longer 0. No longer 0. Do you understand? So the way I take a coordinate is different. Yeah, not good. So it's skew symmetric, I and j. Maybe epsilon ij. This is also okay. Epsilon ij is not good, sorry. Okay. It's not T. So this is no longer 0. So therefore, once you take diagonal combination nice way, it's no longer 0. Okay. So Lagrangian submanifold is that if you restrict the symplectic form in the submanifold, a half-dimensional submanifold, it's no longer 0. It's 0. It's no longer symplectic form. Okay, that's the thing. So some example of the Lagrangian submanifold is given a Cotangent bundle. Here, this one is always the Lagrangian. It's called 0 section. So in other words, you have the Cotangent bundle is n and d star n. 0 section means 0. This is 0 section means just a original one. This is Lagrangian. Okay. Of course, you understand, right? So in locally, always dq in symplectic form can be written as dpi, dqi. Okay. simplex form. And the q direction is just n, and p direction is the fiber. So therefore, once you restrict yourself, you end up with a similar situation with here, this orange one. Okay. And then there's a theorem by Weinstein, theorem by, anyway, Weinstein or Weinstein, Weinstein or Weinstein. I don't know which one is correct. American always pronounce like a Weinstein, but I'm not sure this is correct pronunciation. Anyway, he's a famous simplex geometer. So given a simplex manifold, so this is simplex manifold, and like L is a Lagrangian submanifold. Physicists call Lagrangian as a, anyway, let's not talk about it. It's called A-brane. Physicists call A-brane. It's a brane. Okay. So given a simplex, so what I meant is given a simplex manifold M and Lagrangian submanifold L, and if you look at tubular neighborhood, it's a tubular neighborhood around L. I call it U. So this U as a simplex manifold is equivalent to T star L. As a simplex manifold. So U omega restricted U is omega, which is standard one as a simplex manifold. So this is Weinstein theorem. This the Weinstein tubular neighborhood theorem. This mentioned as follows: given the Lagrangian submanifold inside a simplex manifold, locally around here, around the Lagrangian submanifold, it's just cotangent bundle. Okay. That's what it means. Okay. So this omega is the original simplex form, restricted tubular neighborhood. So therefore, tubular neighborhood Lagrangian itself can be understood as simplex manifold. This simplex manifold U is indeed, as a simplex manifold, is isomorphic to the cotangent bundle of the omega. So therefore, around here it's just cotangent bundle. It's just cotangent bundle. Like given the Lagrangian simplex manifold, around if you zoom into the Lagrangian submanifold, it just looks like the cotangent bundle. This is the Weinstein tubular neighborhood theorem. Weinstein, so Lagrangian submanifold is a very important object in simplex geometry. And then, so Weinstein, how to say, put the slogan of everything in simplex geometry, advertised slogan. Everything in simplex geometry is Lagrangian submanifold. But nowadays, people call, maybe it's better not to say, but more than Lagrangian, it's called co-isotropic submanifold. It's co-isotropic submanifold, but I'm not going to explain what the co-isotropic submanifold is. Okay, let's take a break, and from this preparation, I will connect to the classical mechanics half of the lecture, the later half of the lecture. Okay, if you did the homework, just submit to there, and you can pick your homework over there. Okay.
这个 T 的
然后这个是1，然后这个是1加0，对，这个是1，这是2。这两个。
I need to steal some color chalk from somewhere.
第一个就是
两个是应该它是做
但是第一个是铁，这是零，但都是 Q 的平面。
这二号是1的，就是分别的作用还是先两个乘起来，然后看这样。
就是这两个怎么同样，两个它是同样的，
你看我现在随便一找，
这边一定要有 T 的，这边一定要有，这边一定要有 T 的。
对，相当于这个是缩倍的，对，它是就相当于0。行。营运里面就是这样营运的，对，这两个，这点的就是这样。那个高偏商业的，它是每交换一次会是多少？
How are the hormones? Is it okay? Difficult? Yeah, if you have a question, just tell me. No. You said we do not so much question, not so many. So then homework. So for instance, it's easy. Sorry. This is bad. Homework. It's easy to show that. For sphere, it's easy to show that the geodesic is great circle, particular great circle, and since SON is the isometry. I mean, just briefly. I mean, the lecture doesn't start. You can just stay relaxed. I mean, you can just show that the some great circle is a geodesic. So. And then the rest of the case can be just obtained by just using SON rotation. Similar way, so you just hyperboloid, hyperboloid. It's easy to show that the some geodesic, this one, like for instance, you just cut in the middle. It's easy to show this one is the this one is geodesic, and just use the Lorentz transformation, whatever. I already forgot how I tell it. So you just look at the hypersurface inside of this one. Sorry. In Minkowski metric, right? dx squared, dy squared, dz squared. And you can just do the Lorentz transformation for this Lorentz transformation of this geodesics to find all geodesics. So everything just can be computed by using Lorentz transformation inside of SO 1, 1, 2. That's also one way to show the. And then since this Poincare disk is just a the pullback of the metric, so it's easy to given the geodesics of if it is a pullback of the metric, geodesics map to geodesics. That's definitely true, right? Geodesics map to geodesic, so you can easily obtain the geodesic of the Poincare disk. Yes.
I want to know if the Simplex Group is just the metric of Simplex Manifold.
It's not. There's no metric, but it just preserves simplex form.
But what is the difference between this group and the metric? I think the matrix G.
So G is symmetric. You always need to have xi cross x like this way. So it's symmetric under the differential form. So therefore, when you have G xy is equal to G yx. On the other hand, omega xy is minus omega yx. So the simplex form is different from metric, and oh, I shouldn't use G here. So maybe given the SPN, I call R. Given the element, let's call L star of standard metric omega is equal to omega. So omega is just a sum of dpi, which dqi. So it's more like it preserves the standard metric of R to N. Yes. So it's a bit different from So SON is just preserved metric. So given the SON in the element L, L star of G is equal to G, where G is just a sum of dx I, dx I runs from 1 to n. Do you have a question? Shall we start? Oh, by the way, did I? So you can already see the homework 5, right? So homework 5, so I hope most of them you have already submitted. So from here, so you have a 80%. So the Poincar disk, the metric is given by, so you can use this fact. This is the metric for Poincar disk. Maybe I use UD in the homework. I already forgot. U and V. So therefore, as you approach to the boundary of disk, so the denominator becomes very small. Okay. So therefore, if this tiny length. So you, I think you, right? You mentioned about the Escher's work. This is exactly what the Escher has drawn, the geodesics and so on. But yeah, anyway, so I bought this. I should have brought the Escher's book when I bought in Amsterdam. No, Amsterdam, his museum. Unfortunately, I just came back from Beijing last night in the midnight, so I couldn't go to the office today. So maybe next time. Next lecture, I will bring Escher's book. So therefore, the segment, very tiny, look like tiny segment in standard metric plane. On the boundary is the same. Indeed, it's the same length as in the so. And also geodesic is just it's called sometimes it's called whole cycle. It's just intersection between circle and also line. It can be a line if it goes through at the origin. Okay. So that can be just. I mean that's easy, right? So, I mean I wouldn't say easy, but. I mean, this line, it's easy to see this one is the geodesic because, I mean, in the upstairs, the hyperboloid, if you intersect the plane in the middle, the hyperboloid, this is just really geodesic. I mean, that can easily show. And just use the Lorentz transformation. It's a induced metric from just Lorentz metric, right? Lorentz metric. So it's a space-like hypersurface, so therefore it enjoys the Lorentz transformation becomes the isometry. So therefore you just look at how the Lorentz transformation acts on this geodesic. Okay. So in other words, how this plane is moved under the Lorentz transformation. That's you need to look at. That's how you find geodesic. Anyway, you have to do. The reason why I told you the answer is that the problem 2 is very important. You have a question? I see. So his question is that I think, as far as I understand, so his question is about the Riemannian manifold. his question is that the so in action of the particle, whatever particle along the in the curved space-time is just a dt. I just written the gij dxi. So this is the action I have written in the lecture note. So this will give you length of the manifold. I mean length of the path. And you just consider all possible paths to one point P1, P to Q. And then, anyway, that's the length, the energy of the path, or whatever action of the path. And his question is, I think, is dt. Can you replace gij dxi dt dxj dt without square root? Is that the question? So the question is, his question is there any we can just get rid of square root as action? Yes, definitely you can do. Definitely you can do. And you get the same geodesic equation. But as action, it's different. So this is no longer length. This is no longer. It doesn't give you the. It doesn't give you the length of the path, but order. So one can easily show that it gives you order Lagrange equations the same order Lagrange equation. That can be easily shown. But as action, I mean, if you go to path integral, definitely you get different partition function. But anyway, so to derive a geodesic equation, you can use either of them. Is it unfair? Does it become unfair? Is it okay? Okay. So the reason why I give you the answer for the metric Foncadisc problem 2 is very important in this homework 5. So now, given the, I already forgot how to do that. I think as far as I remember, you have to, given a Foncadisc, you need circle, you have another circle you need to use to swap to the upper half plane. And find it in this metric. So I decided to talk about the modular space in later. Maybe after Lie group and Lie algebra. So I will talk about a bit about modular space before jumping to vector bundle, because modular space becomes very important and people just keep asking what is the modular space, what is the modular space. So I will talk about the modular space a little bit. And this is very important example. So you have to, problem 1 is just a calculation. So, but problem 2 and problem 3 is very important. And I'm going to talk about something related to problem 3. So, from now. Already. Okay, so how the simplex manifold is related to Hamiltonian. So any smooth function h, so given a simplex manifold, so h is some function of the manifold, and then we just define a Hamiltonian vector. So this is called Hamiltonian vector field. It's called Hamiltonian vector field. Define vector field which is really the element in this section of the tangent space of H is defined as follows. Inner product of H omega is dH. So this is the Hamiltonian vector field. So this inner product is defined by as follows. So so this can be understood as a one form, as you can easily see. So right hand side is clear one form, right? dH is one form, so this is one form. This is two form. Omega is two form, but you just contract given any y in the vector field. So H omega, this is one form which acts on y is just a omega xh y up to sign. I don't know, remember sign. To be honest, maybe minus sign will be involved. I don't remember. Sorry. You should take a look at the proper definition with in Nakahara. No, whatever. I prefer Morita's book, but yeah. So this is the definition. So therefore, this has to be equal to dx dhy yh. Okay. So this is how you define the Hamiltonian vector field. So locally, so given a simplex manifold, so as I mentioned, given the point x locally, so one can introduce the coordinate. Unfortunately, I couldn't steal the color chalk from somewhere. Locally, you can take P and Q, and maybe I should use P here and Q here, such a way that the omega is sum of dq. So locally, the local coordinate is P1 dot Pn, P1 dot Qn, and the simplex form is dpi, which dqi. I runs for 1 to n. Okay. So locally, this double theorem tells us you can do that. So therefore, if you write down the local coordinate xh as a local coordinate, it's easy to do. So dh is local coordinate is dx dqi plus partial h pi dpi. Okay. Therefore, so therefore, xh can be written as the up to sign. I think it should be as a vector field. I already used Einstein convention of sum over I. So locally, you need to swap, because I mean you just contract once you contract with delta p with this one, what you get is dqi, right? And delta h. So my convention is minus. Sorry. Then my convention is minus. My convention is minus at this moment. So once you put delta qi with here, you need to have a minus sign, and then you have a minus sign, and you get this one. Okay. Do you understand? You get this one. So if you contract with this one, omega with this one, you get this one times dpi, and which is this one. If you contract dpi, you get dqi left, dq. So del h dq dqi will be obtained from the contraction with this one and this one. Okay? You understand? Okay, let me move on. And then let's consider flow. So given a vector field, you can consider flow if this. So flow of the vector field. So from here, as you can easily see, the flow, it becomes like this way. Flow. It's called Hamilton flow. Hamiltonian flow or isotropy, whichever. Is the equation just given by, dqi dt is equal to ddt dt is equal to with minus sign, and you already look at you already have seen this equation. Okay, so this equation is nothing but the Hamiltonian canonical equation. So Hamiltonian flow in Simplex Manifold is exactly the same as equation motion. So moreover, one can define Poisson bracket f and g. So given that f and g are the function over the m, so you can just define as follows. So let's look at locally. So locally, omega is just a dp wedge dq. Okay, I'm going to omit all the summation variable, and the partial f and it's just a dqi dollar pi plus f dollar pi dollar qi, and then you need a minus sign or here minus sign. And then we can do the same thing for here. Okay, and then let's contract with one by one. If you contract with this guy, this guy should be here, so therefore what you get is minus partial f delta qi delta g delta pi. Okay, and the other piece, if you contract with this one, what you obtain is the del f del pi del g del qi. Okay. You understand? You have a minus sign here. You get the minus sign here, but minus sign counted with this one. This is exactly equal to what I have been written in this is the Poisson bracket exactly. Okay. So yeah. So this minus sign cancels with the opposite order, right? Ordering of P and Q. So again, using simplex form and vector field associated function, one can define Poisson bracket. So Poisson bracket is defined on the simplex manifold. In other words, and then it has a similar property of the commutation relation D bracket, commutator of the vector field. So as you can see, I'm already exhausted. Yeah. Jacobi equation. I mean, so Jacobi and then company, Poisson and so on, those big name is everything you just studied in classical mechanics. And Leibniz rule, yeah. Sorry. Okay, so this is the property. So this is antisymmetric. This is Jacobi identity. This is Leibniz rule. I'm not going to write a word. So let's. Therefore, as you can easily imagine, so this is exactly the same property as the Lie bracket of the vector field. So therefore, as you can easily imagine, so one can easily show is XFG. Okay, so the bracket is really give you the function to function. So the Poisson bracket will give a function, and this function, Hamilton vector field associated with this function is just the Lie bracket of this each Hamilton vector field. Okay, that's easily you can see, and also. So given a so given a simplical manifold M omega and a Hamiltonian. So Hamiltonian is just function, and you have the given a vector field. So this is Hamilton vector field XH. That will generate a flow. So that will generate a flow, Hamiltonian flow, I have written there, that satisfies locally this equation. Okay? So locally means that locally if you take the neighborhood and then again Q and P, and then Hamilton vector field, Hamilton flow is something like Hamilton flow is really push the coordinate like this way, whatever. Okay. In locally this way, and this flow is just a simplex morphism. This flow is simplex morphism, and omega is simplex morphism. Well, this is associate H. Sorry, associate H. This is Hamilton flow. Okay. And then so I mean it's just one parameter family of different morphism. Okay. So one can just compose, let's see, phi t dot f. Okay, phi f is a function. C to m. So therefore, the map from m to r, right? M to r. Okay. So therefore, so one can compose m goes to m. This is phi t, and to r by f. This is the composition, and you can just divide it by ddt. Okay, ddt. So this I call it df dt. This is the meaning of definition. df dt, and this is equal to rho generated by function is equal to, of course, this is hx of f. So this is the definition. Okay, this is the what we have learned what we have learned in the previous lectures, and this is equal to, you just plug it into here, so this is equal to what? Sorry, I'm always tired. So this is equal to f. What I'm doing here? But that's fine. So therefore, okay. So now I understand what I should do. df xh. Okay, df xh, and then so this is equal to I xf omega that acts on xh. Okay, and this is equal to omega f h and minus. Okay. Sorry. xf xh. Okay. So then plug this one into definition here, and that is equal to minus sign mistake. Sorry, plus, somehow plus. This is plus somehow. I think there's no notational mistake I did. I think I need to fix the sign. In lecture notes, sign's wrong. Sign's wrong. I think sign's wrong. I think everything should be, instead of I keep writing dp dq, I think I should change to dq dp. Sorry, but you just put the minus sign in your note. Everything. You just put the minus sign in the note. Okay, but that's why I make a mistake. Okay, I need to change. Sorry. Okay. Okay, I will change later. But in the homework, you can pick whatever convention you prefer. I don't care so much about sign. Yeah, the reason why is that actually in section 7.1 is not written before. I have added section 7.1 by using. Okay, so therefore what you get is the df dt is equal to minus hf. So this is the Hamiltonian equation I have written down, but up to sign. So in the beginning I just written down like this way, right? I think if I use this simplex form, I will get this one, I guess. If you use this simplex form, I will get the upper one. Okay. So let's go back to my lecture note. What I have? Yeah. So the below 7.1 equation 7.1, I have written this equation, but there is a sign here. So that's the reason why I just swap one to the other in the middle. So I will change, but you understand what's going on. So this is the Hamiltonian equation by using constant bracket. So therefore, so the conservation conserved quantity commute with Hamiltonian. So if you commute with Hamiltonian, df dt is equal to up to plus minus hf equal to 0. Okay? So if that means commute, okay? In terms of Poisson bracket. If they commute in terms of Poisson bracket, they conserved. So its time derivative is 0. Okay? So that's what it means. So in other words, even if the function change along this purple line, the body of function does not change. Okay? That's what it means. Okay, so now, everything using simplex geometry, Hamiltonian, Legendre, Poisson, Hamilton, and also Cauchy have done can be formulated everything in terms of simplex geometry, simplex manifold. So therefore, this is called Nether theorem. Okay. This is called Nether theorem. Okay, we have 30 minutes. I'm very glad to have 30 minutes for. Now, very important theorem for classical mechanics. Actually, who teach classical mechanics to you guys? Which book did you use? Is Chinese book? Goldstein? Huh?
Own lecture notes.
What?
His own lecture notes.
His own lecture note. Personally, I have, when I was first year student, younger than you were. I learned classical mechanics by using London lectures. And then later I realized the simplex geometry is related to the. At that time, I didn't study so much about the so-called. I studied Hamilton-Jacobi. I didn't understand. I understand Hamilton-Jacobi formulation of the classical mechanics, but I didn't understand the importance of Hamilton-Jacobi formulation. After reading this Arnold's book, it's a wonderful book. I realized the importance of this Hamilton-Jacobi, also angle action variables. And this is the importance comes from the so-called Arnold-Levy theorem. So this is very important theorem. This connects to simplex geometry to integrable systems, so-called. So let's consider the set of function xi, c infinity of m, such that they are all mutually commuting in terms of Poisson bracket. So of course m omega is simplex manifold, and then the Poisson bracket is coming from simplex structure, and all commuting. And furthermore, we are discussing such a situation. For any point x. So this means that the hi and the hj are distinct as a function. Okay? So they are not same. So if they are same function, it gives you 0. Okay? So they are different, and that's what it means. So, and as you can easily imagine, what is the maximum number of commuting function? What is the maximum number of Poisson commuting function? Just look at the local geometry, local expression. What is the maximum number of Poisson commuting function? And tell me why is the reason. How many Poisson commuting function? Just simply think how many. So given the local coordinate p1 dot pn, and Q1 dot to Qn. Who are commuting?
P's and Q's.
Huh?
P's and Q's.
What do you mean P's and Q's?
I mean, PI and PJ are commuting.
Yeah.
And QJ are commuting.
So they're commuting, right? They're commuting. And also another set of mutually commuting quantities Qi. The maximum number of commuting function is n. Okay? Do you understand? In other words, if you set this hi is some constant, okay, that each function determines some hypersurface inside the simplex manifold. Do you understand? So let's consider Rn, R2, R4, and then P1 is equal. Let's see, P1 is equal to constant. Is just a. I mean. It just it just specifies some slice, right? Slice. Okay. Pi is constant. It's just P1 is constant, some slice. P2 constant is also some slice. Okay. Therefore, maximum number of Poisson commuting function is equal to some constant we determine Lagrangian. Okay. Okay. That's why the Lagrangian submanifold has to be half dimensional. Okay. And the co-isomorphic submanifold is determined by some number of Poisson commuting function. Anyway, so that's a different issue. Okay. So if simplex manifold has maximum number n mutually commuting functions, then it's called completely integral. Complete integral system. I will tell you what it means. Okay, maybe I think I just need to write down. Okay, I will stick on maybe I will stick on this convention. Maybe I will stick on this convention. And just change the last part, the minus sign, just omit the minus sign in front of here. I will omit the minus sign in front of here. I will stick this convention then. It's better to go into classical mechanics. Anyway. Yeah. So the unknown limits are tells us under that situation, completely new simplex manifold. So given a mutually commuting Hamiltonian function, so this is mutual commuting. So this one will map m equals to r to n, right? So and of course this is Arnold limit, Arnold equilibrium. And then just look at this. Let's call this map is called pi. So under the pre-image of some whatever constant point, some point in Rn, point in Rn, pre-image of the function point in Rn is isomorphic to, is indeed topologically equal to Tn and Lagrangian submanifold. Okay. Tn is indeed S1 cross S1 cross n copy. So this is P is called generic point. I pick generic point. Generic point means that it's non-singular. Okay. So this map is non-singular. Okay. Its rank is n. So it's a very simple statement. So given the manifold M, whatever manifold, simplex manifold M, you just map to, by commuting a Hamiltonian, 1.hn to Rn, okay? Rn. And pick a point, whatever point it is, whatever point in Rn, so some generic point, its pre-image is somehow becomes torus. It's S1 times S1 times S1. And those purple point will map to this only purple torus will map to the point. So every point is mapped to the. So every point on a torus will map to the point here. And moreover, if you restrict yourself, the simplex form is restricted in this purple circle. This purple circle, or Tn, is equal to 0. Tn, sorry. Tn is a Lagrangian, this purple circle. It's a Lagrangian submanifold. That's a theorem explanation. I will explain what it means. So let's consider simple coordinate. I think this is very deep theorem, very deep theorem, and I would give you meaning of this example. So let's consider the harmonic oscillator. I don't like harmonic oscillator, Hamiltonian. I mean, when I meet. There's lots of students who wants to come to my group and so on, even from other university. Always ask a simple question to students. For instance, write down Lagrangian Hamiltonian harmonic oscillator. Many students cannot write down even Lagrangian Hamiltonian harmonic oscillator. So if you want to study physics, you should be able to write down Lagrangian Hamiltonian the harmonic oscillator. Sometimes people do not know what harmonic oscillator means. So you guys should know about this terminology. Okay. To be honest, I don't like omega, but let's introduce omega for time being. Anyway. So this is the Hamiltonian harmonic oscillator. I already forgot how to say in the. I cannot write down this one. And then what is gen in the beginning? What is the harmonic? Yeah. Okay, I cannot write down. In Japanese, actually, it's this one actually, but somehow it's in Chinese a bit different. Anyway, so let's consider this system. So what is the conserved quantity? H is the conserved quantity, and the phase space is just two-dimensional. So let's consider simplest example. Simplest example we know. So this is the usual Simplex manifold. The very simplest example. And the Hamiltonian is this one. Hamiltonian, so the particle moves along the constant locus of the Hamiltonian. So what is the constant locus inside a phase space? Huh? So it's called ellipse. I mean, if omega is equal to 1, it becomes just circle. But non-zero, it's just, if it is non-zero, it's just so this is H is constant locus. So now it's already, you can see the connection over there. So if you try to simplify the problem, M is R2, in this case N is equal to 1. What is the most? N equal to 1, so therefore Hamiltonian is only 1. And the pre-image function H is a Hamiltonian. That map from R2 goes to R as a function. Hamiltonian is function. And the pre-image constant. Generic point is the generic point is not point is which is not 0. Okay? If it is 0, it becomes point. So that's not called generic. Okay? So generic point is no longer not 0 point. If you look at the pre-image of the point under the Hamiltonian, it just becomes circle topologically. Okay? Then we need to call to, so since the Simplex form of this one, it's a bit hard to see this is Lagrangian now. Okay? This is hard to see Lagrangian now. Therefore, we need to do the coordinate change. Okay? So as you can easily see, so you just solve so in this case, Hamilton vector field look like what? How does Hamilton vector field look like? This is a Hamiltonian, and you just solve Q dot is equal to this one is what? P. Good. And then P dot is equal to minus partial delta H del H del Q, which is what? Omega minus, good, thank you very much, omega square Q. Okay, you just need to solve this one. So as you can easily see, what is the Hamilton vector field at this point?
It's tangent.
Good, tangent to here. Hamilton vector field. So Q dot is given by P, and P dot is given by minus omega square Q, and therefore it's just tangent. So the Hamilton vector field is tangent to this ellipse. This is the Hamilton vector field XH. Therefore, so you can draw the Hamilton vector field in like this way. Okay? Like this way. Okay? therefore, you can solve easily. What is the Q? Q is equal to square root to H omega sine omega sine phi. P is equal to H omega. So let's go. So I is just H is equal to I. I is some constant. I is some constant. Let's use, instead of H, let's go I. So this is cosine theta, and I need to put some square root. So this is a configuration for Hamilton flow. Okay. So Hamilton flow is something like instead of T I use phi. Okay. Instead of T I use phi. And so we just consider, so this coordinate, it can be understood as a coordinate transformation. So this P and Q can be understood as a coordinate transformation I and phi. Phi and I. So this is called action, angle action coordinate. What is it called? Angle action coordinate. Angle action coordinate. So this is angle. Phi is angle of this Hamilton vector field, Hamilton flow. I is the indeed Hamiltonian. Okay. So Hamiltonian will show up as an action in classical mechanics. I will explain a bit more detail, but this phi and I is called the angle action coordinate. Okay, so you can do the coordinate transformation of PQ to phi I, and see what's going to happen in this simplical form. Okay. So you can just do the coordinate transformation. So dq is what? dq is what? Oh my goodness. I'm already dying. So let's see. dq is what is dq? 2 omega. And then what is 1 over 2? 1 over I sine theta sine phi di plus I cosine phi d phi. Am I correct? Just correct me if I'm wrong. dp is equal to square root to omega. Next is what? E 1/2 di square root I. Next is cosine phi plus what? Next is square root I. Derivative of cosine is minus sine theta, sine phi. Sine phi d phi and minus sine. Is it correct? Yeah, I'm not good at computation. dp which dq is what? So let's look at step by step. dp which dq is d phi. di which d phi, and the cosine square. Okay, and then I cancel. There's a 1, and there are 2 appear, but 1/2. There's a 1/2, so therefore this one, and plus another piece will come here, sine square, but now it's d phi which di. Okay, so therefore you have sine square phi di which d phi. Therefore, this is di which d phi. Okay? Do you agree? So therefore, in the action angle action coordinate, the simplex form transform like this way. And as you can see, so this ellipsoid, I is just constant. Okay? I is constant. So therefore, you can easily see it's Lagrangian. There's no variation. Okay? So therefore, it's just a Lagrangian. Omega simplex form is 0 if you restrict yourself to here. Okay? Okay. So that's what you mean. Arnold-Levy theorem. Okay? And this is a very simple example. But problem 3 in homework this week, problem says, I just give you the famous problem in the Kepler's planetary motion. That is the most famous example which can be solved by using Arnold-Levy theorem. So you should derive first, second, third law of Kepler. Have observed by looking at the planetary, the very primitive, scope. In hundreds of years ago, what Kepler has done, by using simplex geometry, you have to derive. Using Arnold-Levy theorem, you have to derive first, second, third law of Kepler's law. That's a problem 3. So it's a very, very, very interesting, important problem for physicists. So I will give you, if you solve, I will give you 10 points into the problem 3, and the rest of it is 5 points. So it's more than 10 points. Okay, so why it's called integrable? So let me finish this story. Let me finish story. So the Hamiltonian equation is phi dot is equal to dh. So yeah, so now h can be written. So we should write down everything in terms of I and phi. H can be written in terms of just I. Okay, it's just some proportion to I. Okay, so then Hamiltonian theorem is given by. So Hamiltonian equation is this one. Omega I dot is equal to minus h phi is equal to 0. Okay, so as you can see, under the equation motion, I is constant, and phi dot is just omega. Okay, it's what you have learned in harmonic oscillator. It's very simple. I would say simpler than this one, right? Simpler than this. So action angle coordinate is very simple. Why is it called action? So therefore, so from this equation, you get phi t is just sum phi 0 plus omega t, and then it is just constant. Okay. It's just constant, or it just maybe you should physicists should write energy divided by omega. Okay. Why is it called integrable system? Let me finish my story. So let me finish my story. So let's consider the following thing. Sorry. PDQ. So this is called Levy form. So if you take the Levy form dPdQ, what you get is simplex form. Okay? Simplex form. So this is called Levy 1 form. Let me finish. I mean, if you want, you can leave, but let me finish. 1 over 2 pi, and you just put the equation motion. 0 to 2 pi, p. So you need to write down everything in terms of I and the phi. Phi. So you just plug that one into here. Okay. So let's plug that one into here. So P is square root 2I omega cosine phi, and the dq is over there, right? Dq is over there. So 1/2. Since we'll only look at this integral is along this ellipsoid. So what we are going to do along the ellipsoid. So the di is equal to 0. So therefore we just look at the d5 piece. Square root I to I omega cosine phi d phi. Okay? PDQ, PDQ is this part. You just essentially integrate over this area. That's what you mean. Okay? PDQ is. And then if you go into this action angle action coordinate, what you get is just a very simple cancellation. You will see is indeed 2I cos square phi d phi 0 to 2 pi. And if you perform this integral, what you end up is equal to I. Okay? Which you end up is I. So therefore, you can integrate PDQ. Okay? Exactly. Along the motion of the harmonic oscillator inside a phase space. Okay, phase space. So you need to consider phase. Both include Q and P. Momentum and coordinate. So this phase space. In phase space, one can integrate out this quantity, leave it one form. That's why it's called integrable system. Let's stop here.